Okay.
Isn't it nice when things just work?
Okay. This is the blurb that goes with that little video. There are no computer graphics or digital tricks in these images. Everything that you see happened in real time exactly as you see it. The recording required 606 takes, and in the first 605 takes, there always was something, usually of minor importance, that didn't work. It was necessary for the recording team to install the setup time after time, and it took several weeks working night and day to achieve this effect. The recording cost $6 million, and it took 3 months to finish, including the engineering design of the sequence. There were only 6 Honda Accords built by hand in the whole world, and to the horror of Honda engineers, the recording team disassembled 2 of them for their recording. Everything that you see in the sequence, besides the walls, floor, ramp, and untouched Honda, is part of those 2 automobiles. The voice is that of Garrison Keillor. I think that's where most of the $6 million went. The commercial was so well received by Honda executives when they saw it that their first comment was how amazing the computer graphics were. They almost fell out of their chairs when told that the recording was real without any graphics manipulation. So this is what you call a Rube Goldberg, where you make something simple happen. In this case, it was pushing a button in as complicated a way as possible through very complicated transfers of energy, changing kinetic energy into potential energy, and potential energy back into kinetic energy. And so for many years I was a judge of the Science Olympiad that was held every year, and they would have an event where they would have to create a Rube Goldberg machine. And some of the machines that these young middle school and high school students would come up with were just amazing. They would, have a pendulum come down with matches that struck on a striker, and then that would go over some black powder that would explode, and that would melt through some fishing wire that would bring an axe down. It was all very, very dangerous. Come on in. Okay. Would someone be willing to give us an opening prayer to get us started, right? Anyone in the mood? Thank you.
Our dear Heavenly Father, we're so grateful for this beautiful morning that God's blessed us with, and we're grateful that we're able to have come to physics this morning, and that we have this opportunity to be learning and expanding our knowledge and following one of thy commandments. And we are grateful, Father, for the weather and for the beautiful scenery that we have outside. inside. And we ask the Father this morning to please bless our minds and bless our spirits, that we can learn well and that we can have a spirit with us. And we ask that you also bless those individuals who are struggling, that they may get the help that they need by any means. And we love you and say these things in my beloved Son, Jesus Christ. Amen.
Okay. Let's just remind ourselves where we've been really quick. We found that whenever we exert a force in the same direction as the object is moving, we increase the kinetic energy. We say that we have done positive there. When we push in the opposite direction of the motion, we decrease the kinetic energy, and we say that we've done negative there. If we exert a force that is perpendicular to the motion, we do not change the kinetic energy, and we say that no werk is done. And that's why we call it werk instead of work, because that's a very, very different sort of animal than what you would be paid for on a farm. Okay, and so the definition of werk has this complicated three-tier structure where it's positive if they're in the same direction, negative if they're in opposite direction, and zero if they're perpendicular to each other. Now, I've listed here on either side the formula for kinetic energy, gravitational potential energy, spring potential energy, and werk. Now, I really don't want this class to be about memorization. And that's why on the other exams that we've had, I've given you all of the equations and definitions that you need to do the exam. But it turns out that when we're talking about energy, if you don't know these definitions, these formulas, you don't recognize the players on the field. It's like me watching a soccer game. I have no idea why they're running around in their shorts, okay? So what I'm saying is that you will not have these formulas on the front page of your exam. And there's certainly no one over there at the testing center that's going to give it to you, okay? So you have to have these definitions memorized. And as long as you have to have them memorized by the third midterm, you just as well memorize them now. It'll make it much easier to do your homework and to understand what's going on in lecture, okay? Now, we talked about this third bucket, the spring potential energy bucket, and we said that it was 1/2 times the spring constant K times the stretch or compression of the spring squared. And so you see that's always a positive quantity, okay? Now, again, I asked you to trust me that that was the right equation. But today, I'm really excited. Today, I'm going to show you where these equations come from. But first, let's finish this, this little problem we started at the end of class on Thursday. We had this 10-kilogram block that was pushed up against the spring. It's not connected, but just pushed up against it. And it compresses the spring by 1/2 meter. And we said that if that spring had a spring constant, a stiffness factor of 16,000 newtons for each meter, well, first of all, that tells us that that hand is Superman, okay? We asked how much energy is stored in that spring bucket. Well, that's just plug and chug, okay? We plug into 1/2 times the spring constant, and then the compression squared, and we got 2,000 joules. And then we said, well, there's no kinetic energy. If I call this height 0, the table, there's no gravitational energy, so this spring energy is the total energy. and then we release the block. We let go, and it takes off. And remember, these hash marks indicate friction, but where there's no hash marks, that's a frictionless surface, okay? So if I ask how much kinetic energy does the block have at point A, remember I liken this to you starting out a walk across Central Park in New York with $2,000 in your pocket. And you get all the way across and you don't get mugged, okay? Never happened before, but you don't get mugged. How much money do you have? $2,000. And so, since this is a frictionless surface, we didn't lose any energy. So we've still got 2,000 joules, and now it's in the kinetic energy bucket. So that's just the type of question you hope to get on that next midterm. Okay? It just, wow, that's easy. Now I can ask what the speed of that block is at that point, A, and now I can use that formula, 1/2 mv squared, okay? The 2,000 joules is my kinetic energy, 1/2 times the mass times the speed squared. If I solve that for V, again, this becomes just, can you do algebra? I get 20 meters per second, okay? Now, that's the review. We've been there before. We stopped there. And then we got to this point here where we asked, once it reaches this rough patch, we start to hear scraping. And the question is, how far will the block slide past point B before it comes to a halt? And this is, you know, one of the most common energy problems that you'll have to solve. Okay? And the way we solve it is to just use this Grant-High equation. The energy that we start with plus the vert is equal to the energy that we end up with. And so in this case, remember this formula here, okay? If we remember that this changes the kinetic energy, and we call that vert, and then if I just write this as kinetic energy final minus kinetic energy initial, I'm going to rearrange this a little bit. I'm going to bring this kinetic energy initial over to the other side of the equal sign and make it positive. Okay? And then I'm going to trade left and right, just to make earlier to the left, Western society. And what I get is this formula here that says the kinetic energy that I start with is equal to the kinetic energy I end up with, except when it's not, when work is done. Now, in this problem, where we derived this formula, there were no springs. It was on a level surface. There was no gravitational potential energy. Kinetic energy was the only bucket we had. And so, what if I got different buckets? What if I've got the other buckets? Well, then we have to generalize this. And what we get is what's called the vert energy theorem. Again, the energy you start with is always equal to the energy you end up with, except when it's not, and it's usually not, if vert is done. Okay? Now, here's my message to you. This is always the first step of every energy problem. You could go out and just write this at the top of a piece of paper, Xerox that piece of paper 20 times, and make that your new stationery for the next 2 weeks. And every time you have an energy problem, pull out one of those pages, and you're halfway done. Okay, you're halfway done. So, let's use this on our problem. We have 2,000 joules when it gets to point B. When it finally stops sliding, we got nothing in the bucket. The bucket's empty. So how much vert do we have to do to get rid of 2,000 joules? Well, we got to do negative 2,000 joules of Verric, okay? And that Verric is done by the friction force, kinetic friction force. Now, if I draw a free body diagram for this 10 kilogram block, the weight force is 100 newtons, and that means that the normal force by the floor on the block is 100 newtons. And this is the easy kind of friction. It's this coefficient of kinetic friction times this normal force right there. And that gives me 20 newtons. And so if I plug into that Grant-Hyde Verric energy equation, there's my energy initial, there's my energy final, and there's the negative Verric that's done. Negative 20 newtons times the distance. And that gives me a distance of 100 meters. You know, that's a football field. Now that tells you two things, okay? First of all, it tells you that this coefficient of kinetic friction represents a very slippery surface. This thing is going 40 miles an hour and it slides for 100 meters. The second thing that you know about this is that this block doesn't have very good brakes, okay? Folks, when it gets icy and you hit your brakes in your car, does it sound like a machine gun's going off? Okay? Okay, that's what you want to hear when you hit your brakes. Okay? If you don't hear that, you need to have a heart-to-heart with your parents and ask, why don't you love me? Okay? Because what's going on is that the braking system is grabbing the calipers to slow down the car, but when it feels like the car is going to start sliding, it lets go. And then it grabs again and pushes until it feels like the car is going to slide. And that's because we want static friction to stop us on the road, not sliding friction, because that static friction can be greater. See if your neighbor has parents that love them. This is what I was looking forward to. This is where I get to come clean and show you where these formulas for potential energy come from. And it's very, very simple now that we understand Verric. What I'm going to do is set up a situation in which I, as an external agent, do Verric in such a way that I only fill one bucket. Okay? First of all, let's look at a block of mass M that is lifted at a slow constant speed from here to here. And when we first start looking at it, it's moving at that slow speed. And when it gets up there, it's still moving at that slow speed, all the way up. Okay? Now, if I look at the buckets, what buckets do I start out with? Well, I've got some kinetic energy because it's moving. If I call this my height 0, then I don't have any gravitational energy, and there's no springs in this problem. So that's just silly, okay? And so my total energy is just that kinetic energy right there. Now when I get up here, I still have the same amount of kinetic energy, but now I've got gravitational energy, and there's still no springs. So now I've got more total energy. Well, remember, in order to get more total energy, something has to do Verric. And that something is my hand. Okay? So I have to do positive Verric. I have to push in the same direction the block is going. That's positive Verric. Now, all I have to do is figure out how much positive Varric I had to do. Well, that's just the force I have to push with times the distance. Well, the distance is just h, that's easy. What about the force? Well, if this is constant velocity, zero acceleration, I have to push with exactly the force of its weight. Okay? If it weighs 200 newtons, I got to push with 200 newtons to keep it going at that constant velocity. So that means that my force is going to be m times g. That's the weight. And the distance is going to be h. Now that looks familiar, doesn't it? That looks familiar. That's just the formula for filling up that gravitational potential energy bucket. That's where we get that formula. Okay? We fill up one bucket at a time and we ask ourselves how much Varric did it take. See if your neighbor's okay with that. See if they understood what just happened.
It makes sense, but he hasn't put it into question.
Yeah, you got it.
Okay. Well, that worked. Let's try it now with the spring. Okay, let's look at the spring potential energy. And what I've got here is a spring that when it came from the factory, when I opened the box, that spring was this long, okay? And so when I put that block next to the spring is not stretched or compressed, okay? That's just how long it is. And then I'm going to push that block against the spring and I'm going to compress the spring. And this is important. I'm going to start with it at rest. I'm going to push with a slow, constant speed, and then I'm going to stop at rest. Okay? And if we look at the buckets, let's look at the starting point here. It's at rest, so there's no kinetic energy. I'm calling this tabletop zero height, so there's no gravitational energy. The spring is neither stretched nor compressed, so there's no spring energy. So there's no total energy. Okay? Now, when I get it over here, again, I stop it, so there's no kinetic energy. It's still on the table that I've called height zero, so there's no gravitational energy. But now there's spring energy. That's what I wanted to do. I wanted to fill up just one bucket. And I wanted to see how hard it was to fill up that bucket. How much Varric did I have to do? Okay, so I changed my total energy from nothing to this much. And that means I had to do positive Varric. So, let's figure out how much Varric I had to do as that hand. Well, again, that Varric is just going to be the force times the distance. Now the force, again, if I'm moving at a constant speed, I got to push just as hard as the spring is pushing back. And the force by a spring is given by Hooke's law. That's K delta S. And the distance that I compress it is delta S. And so that gives me K delta S squared. Okay? And that's where we get the formula for potential energy for a spring. See if your neighbor's okay. Okay, yeah, just a second, Thomas, right? Thomas. It's a half. You're gonna beat me up over a half? Yeah, it just seems like that's kind of nitpicky, don't you think? Yeah. Okay, let's talk about that half. Okay? That's the force exerted by a spring, but only when the spring is already compressed by delta S. So that's how hard the spring is pushing here. Okay? But when I started out, the spring wasn't compressed at all, and so the spring wasn't pushing at all here. So if I think of what's going on here, it's really easy at first, and then it gets harder, and then it gets real hard, and then it gets very hard. Okay? So which force do I want to use? The smallest force or the biggest force? The average. And the average is halfway between those. Okay? The average is 1/2 K delta F. And so I don't want that formula up there. I want the average force times delta S, and that's where that half comes in. Thank you very much. Okay? I did not pay Thomas one dime. Okay? But I appreciate his help. Okay. Everyone feel comfortable with that? That's where we get that formula, 1/2 K delta F squared. Good. Now, I'm here to tell you that if this were the 121 class, the class that the engineers take with calculus, they would go through an equation that involves integration to get that same formula. And if you've got to use calculus to come up with that formula, you're just not doing it right. Okay, you're just not thinking. Okay? Now, that's the formula for the change in that potential energy bucket. Okay, let's look at this loop-de-loop here. What we have is a Hot Wheels car, and it just goes around and around. And the question is, as the marble, I tried it with a wooden marble and it just kept leaving the track, so we did it with a Hot Wheels car. If it's a frictionless loop-de-loop, does the mechanical energy increase, decrease, or stay the same? You know the answer to this. Let's just all get it right, shall we? Everyone get this right. Okay. Are we done? Is that everybody? Last call? Okay, if we all get this right, we're going to Disney World. Oh, no. Those people have my back. At Christmas time, I'm taking 27 people to Disney World. It's essentially my yearly salary. But, you know, you only live once. Okay? Okay. Because it's frictionless, the only force that this track can exert on that car is a normal force. And the normal force is, by definition, always perpendicular to the track. And the car, by definition, always has to go parallel to the track. And so the force and the displacement are always 90 degrees to each other, and that's zero var. And if there's zero var, then the energy is conserved. Okay? Now, I have an old exam question that I'm going to hand out. I need my helpers. Where are they? Where are my helpers? Okay. There's a helper. Thank you. Thank you. Another helper over here. Come on. Okay. Oh, Brigham Young University, Hawaii. Oh, man. That's where we all wish we were. On the beach. Okay, raise your hand if you still need a handout. Is that an extra one?
Or hold the rest of our road. Got it.
Thank you very much. Thank you. Okay. In this problem, a block of mass 10 kilograms slides down from a frictionless ramp, such that the center of the block drops a distance of 0.8 meters. As the block passes from point B to point C, it encounters a 2-meter section of track that is rough, having a coefficient of kinetic friction of 0.3. After passing point C, the block compresses a spring and comes to a momentary stop. In the questions that follow, consider the block earth spring system and assume that G is 10 meters per second squared. Okay, so the first question is really easy. And when this was an exam question, that first question was only worth 2 points, kind of signaling that this is an easy question. And it turns out that most people got one of those 2 points for saying, oh, the work, first of all, you misspelled it. It's Werk. So the Werk is 0. But they forgot to explain their reasoning. And their reasoning should have been, the normal force is always perpendicular to the motion, and so it does no Werk. And then we're asked to find the kinetic energy of the block at point B. Now, if we give us some board space here, I posted a solution to this exam question, and my solution for part B said that the kinetic energy at point B was equal to mgh. And my students came unglued. They said, Greg, you lying sack of spit. You told us kinetic energy was 1/2 mv squared. You made us memorize that. And then on the exam, suddenly it's mgh. That's not fair. Well, what I had done, my real crime, was skipping a step. What I should have said was that the energy at A was equal to the energy at B plus any Werk that happened between A and B. but because there's no friction, that would be 0. And so then, I would say, well, the energy at A is mgh at A, because it's not moving at A and there's no springs yet. It's just gravitational potential energy. And the energy at B is all kinetic, if I call this level 0. And so that's where the formula came from. In other words, I know how much gravitational energy I had, and I wasn't robbed, so now that's all in the kinetic bucket, okay? And so I ended up with kinetic energy at B was equal to, the mass of the block was 10 kilograms, G is 10 newtons for each kilogram, and the height was 0.8 meters, and that's going to give me 80 joules. Okay? Does that make sense? Okay, so I've got 80 joules, and put that up there. 80 joules. And that means that I still have 80 joules at B. And then we're asked to find the magnitude of the frictional force by the rough section of track. Now this you should be able to do this in your sleep. Anytime you're asked for any force, go for a free body diagram. I have a wake force of the block is 100 newtons. Because it's on a level surface with no acceleration up or down, that's going to be a normal force by the track on the block of 100 newtons. And this is going to be the friction force. Kinetic friction is equal to mu sub k times the normal force, but the indices have to be the same. And so this is going to be 0.3 times 100 newtons equals 30 newtons. Okay? So that's the answer to part C, 30 newtons. Find the kinetic energy of the block at point C. Well, again, if I start with that grand high equation, energy initial plus Verk is equal to energy final. I'm looking for the kinetic energy at C, so I'm going to make that my final point. It doesn't matter whether I take the initial point to be point A or point B, it's 80 joules either way. Okay, so I'm going to take that at point B. And so I would have 80 joules minus 30 newtons times 2 meters is equal to, the only energy I have at C is kinetic energy. And so essentially, I started that rough patch with 80 joules of energy. I got robbed by 60 joules, and so now I have 20 joules left over. Okay? See how easy these energy problems are? The last question says, if the spring has a spring constant of 160 newtons for each meter, find the compression of the spring when the block comes to a halt. Okay? So, how do we do that? Well, let me go over here. This is part B. So again, I start energy initial plus Verk is equal to energy final. I'm looking for the compression of the spring when it stops at the turnaround point. So I'm going to call this my final at the turnaround. Point. And I'm going to call this point C, because I don't want to deal with that rough patch again. Okay? And so there's no Verk between point C and that turnaround point. Well, I know that I had 20 joules at point C. At E, I asked the same 3 questions I always ask. Is anything with mass moving? Not at the turnaround point, you got to stop to turn around. Is anything up off the floor? No. Are any springs stretched or compressed? Yes. And so I have spring energy at the turnaround, okay? And that's going to be 1/2 times 160 newtons for each meter times my compression. In the problem I did delta X. I would prefer to use delta S. Remember to square it, okay? So if I multiply both sides by 2, this becomes 40. If I divide by 160, that becomes 1/4 is equal to delta S squared, and that gives me a delta S of 1/2 meter. Okay? Check that your neighbor followed what we did there.
Right here. Size of the definition. What the heck happened to me?
Are there questions? Okay. Okay. I just want you to know that we can dance these problems frontwards or backwards. I could have asked it this way. A block of mass 10 kilograms flies from rest down a frictionless ramp such that the center of the block drops a distance h. I didn't give you what h was. As the block passes from point B to C, it encounters a 2-meter section of track that's rough, having a coefficient of kinetic friction 0.3. After passing point C, the block compresses a spring by an amount of 0.5 and comes to a momentary stop. Find h. It's no different. You just, initial energy plus Verac is equal to final energy. And your initial would be at point A, your final would be at the turnaround point, and that would be that. Okay? Now, I'm getting to your question, I promise. There's this problem in your homework that was an old exam question, and it was put on the exam in 1998 when Jeff Adams and I were team teaching the course. And we put it as problem 1 because we thought everyone in the class is going to get this right, and it's going to give them confidence to go through the rest of the exam. It's a sure thing. Well, back then we used to grade all of our exams by hand, and it used to take us till 3 in the morning, and we were depressed because everyone was missing this problem, and it was taking them a huge amount of time, so that the exam average was very low. And so let's just look at it and see what the problem was. Tarzan swings on a rope from a ledge that's 5 meters above the lake. The rope's fastened to a tree limb that's 6 meters above the lake's surface. When Tarzan lets go, he's risen to a height of 2 meters above the water. How fast is Tarzan traveling just before he hits the water? Now, first of all, true or false? Energy is conserved in this problem. Go ahead and click.
So I hope so. I think it's just going to be a loser. I think the only way to lose it is
Okay. Last call. The answer is true. Assuming you ignore air resistance, the energy is conserved. Now, the reason for that is that the Tarzan swing is always pulling along the vine. And Tarzan is always moving perpendicular to the vine. So as the swing goes back and forth, the force and the displacement are always 90 degrees to each other. And so that's Verk 0. Okay? So a Tarzan swing never does any Verk, just like a frictionless ramp never does any Verk. Okay? Now, if we look at the energy bucket, Tarzan starts out he's not moving. Okay? So there's no kinetic energy. There is gravitational energy, and that's my total energy. Now, when he lets go of the rope, he still has that same total energy. But now some of it's in the kinetic energy bucket, and some of it's in the gravitational bucket. And right before he hits the ground, right before he hits the water, don't let him hit the water. Right before he hits the water, he still has all of that energy. If you let him hit the water's going to do negative Verk on it. Then it's a messy problem. Okay? But right before he hits the water, all of that energy is in the kinetic energy bucket. And here's my message with this problem. It don't matter what happened in between the initial and final states. He could do a triple flip with a twist. It don't matter. Okay? That goes away. And so all I have to say is that the initial energy is equal to the final energy. Initially, he had gravitational energy. And at the end, he only had kinetic energy. His mass cancels out. I solve for V, and I get a very simple answer. Now, why did all of my students get that wrong? Well, they got it wrong because I gave them too much information. I told them he let go when he was 2 meters above the water. And so what they did all night long was use energy to figure out how fast he was going there. And then they did some fancy trig to figure what angle he was flying at. And then they turned it into a projectile motion problem. And it took them forever when they could have been solving the rest of the exam. Okay? Now, most of you are trying to be doctors and dentists. Okay? And on that MCAT, they're going to ask you questions where they give you information that you're not supposed to use. Okay? You're trying to solve this medical problem. You really don't care what color their hair is. Okay? Now, are there questions on this problem? You see why I thought it was going to be super easy? I just was wrong. Okay? Now, which person strikes the water with the greater speed, A or B? Yeah, the same. Exactly the same. But this person doesn't know what he's doing. This person is having fun. Okay? But they hit the water at exactly the same speed. Okay, Thomas asked a profound, important, wonderful question. And that is, well, why don't we have to worry about the Verk done by the spring? Why don't we have to worry about the Verk done by the spring in that problem that I handed out to you, the old exam problem? Let's look at that. We've talked about 3 buckets: kinetic, gravitational, and spring potential energy bucket. And when we add those together, we get the total mechanical energy bucket. Okay? But we don't always get to use all of those buckets. It depends on what our system is. Okay? If I take my system to just be that block, and in this case the block is actually attached to the spring. But if I draw my red circle just around the block and I say, That's my system. That's what I'm looking at. Well, that block can have kinetic energy if it's moving, but it can't have any gravitational energy. Because gravitational energy is energy between an object. I don't have a heavy object. Oh, here we go. The gravitational potential energy of this little tape dispenser it exists between the tape dispenser and the Earth. The Earth is pulling on it, it's pulling on the Earth, and that's what gives it that energy that we call gravitational potential. If this were out far away from the Earth, it'd just be floating there, and you wouldn't be worried if it was floating over your head, right? So without including the Earth in my system, there's no gravitational energy bucket. Likewise, if I don't put the spring in my system, I can't talk about the spring energy as part of my system energy. And so all I have in that case is just a kinetic energy bucket. Now, if I compress the spring and I let go, watch what happens to that kinetic energy bucket and hence the total energy bucket. Okay? When it gets there, it's moving, so I have energy. When it gets to its equilibrium point, the spring is now the same length that it was when it came from the factory. Now the block's moving its fastest, and then it starts to stretch the spring and it slows down. And then it gets to the turnaround and stops. And then it comes back. So you see, that energy bucket is filling up and emptying, filling up and emptying. Well, what's changing the total energy? The work done by the spring. But the work done by a spring is very complicated because springs push hard or soft depending on how much they're stretched or compressed. And so we don't want to deal with that work done by the spring. So instead, we always include the spring in our system. We draw that red circle to include both the block and the spring. And now if I look at the situation, I can talk about the kinetic energy of the block, I can talk about the potential energy of the spring. I still can't talk about gravitational energy because I didn't include the Earth. But now watch what happens to my total energy bucket. If I compress the spring and release it, well, initially I've got all the energy in the spring, and that's my total energy. And then the spring starts to relax, but now the block is moving. So I've got kinetic, I've got spring, but I still have all the total energy. When the spring gets to its equilibrium point, the length it was when it came from the factory, all of the energy is in the kinetic energy bucket. But I still have all the energy if it's a frictionless table, okay? And then we start to stretch the spring and the block slows down, but I still have all the energy. And then we get to the turnaround point where all of the energy is back in the spring, but I still have all of the energy. So now watch what happens when it goes back and forth. Because that total energy bucket stays the same, is conserved, that I can work with, that I can solve problems with. And that tells me that some systems are more useful than others. When you find yourself faced with an energy problem, your most important decision is, what system should I be looking at? And I want to tell you that when I gave you this grand high Werk energy theorem, I lied. I lied. It's not energy initial plus Werk equals energy final. It's Werk external. External. Okay? Okay. if I were to take this skateboard that is someone else's, and if I were to sit on this, is that okay? Maybe. Okay, if I were to sit on this and push on my back, I'm not going anywhere, okay? I'm going to have to push on something that's outside of my system, me and the skateboard, in order to change the energy. Just one part of the system pushing on another part of the system doesn't get me down the road. Okay. Thank you for bringing that today. Appreciate it. Okay. Now, what should we include in our system? Okay? Every single time, I want you to follow this recipe. I want you to include anything with mass that moves so that you can talk about kinetic energy. Okay? And then I want you to always include the Earth so that you can talk about gravitational potential energy. And then, finally, include any springs in the problem in your system so that you can talk about spring potential energy. Because if you put those in your system, you don't have to worry about the work done by those springs. And the work done by those springs is complicated. It's messy. You don't want to deal with that. Okay? Now, the things that are outside of your system we call external agents. Okay? So what are the external agents? Oh no, not them. No, that's not them. Is that even James Bond to you? Okay? Or is it one of these guys up there in the corner? That wasn't mine. That first. That one. That's James Bond. Okay. Sorry. What are external agents? Well, what should I leave outside of my system? Well, you can always leave Tarzan swings and the frictionless ramp out of your system. Why? Because they do no work. It costs you nothing. Okay? The floor usually does negative work through a friction force. Okay? The lobster hand, which is the only kind I can draw, is sometimes it does positive work, sometimes it does negative work, depending on whether it's pushing in the same direction or the opposite direction that the object is moving. And basically just anything else that's not this, or this, or this. Okay? Anything that's not those three things, leave it outside of your system. Okay, check on your neighbor. Do a buddy check. Okay. Let me help you with this, the last problem on your tutorial homework. This is on the back side of that problem we solved a while ago. You're going to have different numbers in this, but these are the numbers that I'm going to use. I think for some of us, the problem with this question is one of visualization. What's going on here? Well, you've got a pendulum, which is comprised of a 7-meter length of string attached to a bob of mass 0.2 kilograms. I don't know why they're called bobs. I really don't. It could have been called bills. Okay? And it's, let's say that we nail the end of the string to the side of a barn. Okay? And we let go of this, and the bob comes swinging down, and normally it would just swing over to this side. But someone has put a nail sticking out of the barn, and when this bob comes down, dragging the string with it, the string hits the nail. And what happens is that instead of going up like this, it's forced to wrap around the nail. Okay? You picking up what I'm putting down? Okay? You seeing what's going on? Okay. Now, what we want to know is how fast. Well, let's set up our system, okay? Let's set up our system. We want to include in our system the ball because it has mass and it's moving. We want to include the earth so that we can talk about gravitational potential energy. But there's no springs in this problem, so we don't have to include any springs. Now, if we look at that bob at some arbitrary location and draw a free body diagram for it, we have the gravitational force by the earth on the ball, the bob, okay? Now, we also know there's no magnets, so what touches that bob? Well, I've got the string, and it pulls. And that's the free body diagram. I'm done, I followed the recipe. Now, the next thing I do is I ask, which of those forces is an internal force and which are external forces? Well, this force between the earth and the ball, that's one part of my system, the earth, pulling on another part of my system, the ball. I don't have to worry about the Verric done by that. And that's another good thing, something to put in your toolbox. You're never going to need to worry about the Verric done by the gravitational force because you're always going to include the earth in your system. Never worry about the Verric done by the gravitational force. Never worry about the Verric done by a spring. Okay? Now, that's an internal force, but the spring, that's a Tarzan swing. Remember, I always put that outside of my system, so that's an external force. But when I ask, does it do any Verric? No, it's a Tarzan swing. It's always pulling along the string, and the ball's always moving perpendicular to the string. So it does no Verric. Okay? So that means energy is conserved as it goes from here to there. So let's use that conservation of energy to figure out how fast it's going when it gets to the top of this smaller circle. Okay? And again, the length of the string is 7 meters. The distance down from the pivot point to the nail is 6 meters. And so with your clicker, tell me well, first of all, find me a number for that speed, and I'll give you some choices to choose with your clicker in just a moment. But with your neighbor, find a speed. Okay, these are your choices. Oh, I didn't get you started. Whoa, let me get you started. My bad. Okay.
Well, we have kinetic energy, which has velocity. I don't know how to use it.
Okay, if you haven't found an answer yet, just choose one until you get your clicker points. We've got 5 minutes left, and I'm helping you with your homework, so they're important 5 minutes. Last call. Okay. Whoa, we're not sure. Okay, fair enough. Let's talk about it. We said that energy is conserved. If we call this the lowest point in the problem, our height 0, then when I start out at rest, all of my energy is gravitational. And when I get here at the top, I have some kinetic and some gravitational. If I plug in my formulas that I've memorized, I've got mgh for potential, and I've got 1/2 mv squared for the velocity of the top. Since all of those have a mass in them, and this is confusing, isn't it? Because mass is m, and meter is m. And so you have to know from the context which of those m's are mass and which are meters, okay? But the masses can cancel out. And if I plug in the values, what I get is a value of 10 meters per second. And that's just algebra. Yes, sir?
Where did you get the 2 meters from?
Oh, if I call this my 0, and this circle, if this is 6 meters, and this is 7 meters, the radius of this circle is 1 meter. And that means this is 2 meters. Right? If that's 1 meter and that's 1 meter, it's 2 meters above my 0. Okay? Okay. Now, the next question was the magnitude and direction of the acceleration at the top. Well, the ball's going in a circle. So I know that the centripetal acceleration is going to be towards the center of the circle, or down. And the size of that is always v squared over r. Well, that's just going to be 10 meters per second. I got to square it, and then divide by the radius of 1 meter. And that gives me an acceleration of 100 meters per second squared. The next question is, well, what's the direction and magnitude of the net force up at that top? Well, net force is always given by Newton's second law, mass times acceleration. Okay? So if I take the mass of 0.2 kilograms, multiply by 100 meters per second squared, I get 20 newtons down. Now, because we handled centripetal acceleration towards the end of the last unit, this gives us an opportunity to come back and review that. For example, we can ask, what's the tension in the string when it gets to the top? Well, I'm asking about a force. Any force, I draw a three-body diagram. The weight of that bob is just 0.2 kilograms times 10 newtons for each kilogram, or 2 newtons. This diagram also has one other force on it, the tension force, pulling down towards the center. And this diagram has to scream down by 20. And so that means that the tension force has to be 18 to give me a total scream down of 20 newtons. Check quickly on your neighbor and then go to the forum. Okay, go somewhere else.